Let us talk about this problem. We are given an array. We need to find out length of the longest subsequence such that this subsequence has consecutive elements. What do we mean by consecutive elements? Elements in the form of x, x plus 1, x plus 2, x plus I, right? Elements like 3, 4, 5, 6, 7, minus 1, 0, 1. And these elements in the subsequence may appear in any order. You may have 5 first, then 4, then 3. It's still a consecutive subsequence. Let's understand the problem with these examples. Let's say we have this array. Now if you take a look at this array, these are the 4 elements which are forming the longest consecutive subsequence, right? 1, 2, 3, 4 consecutive elements, and the result for this is 4, right? Suppose there was a 10 here, then 9 and 10 would also form a consecutive subsequence, but length of this is 4, right? Individual elements are also one length subsequence. So this is one length, this is one length, and this is 4 lengths. That's why we have the output as 4. Now let's see this example. Here we have output as 2 because 8 and 7 they form a subsequence with consecutive elements. 20, 30, 40. Here we have individual elements only, single element subsequences. Therefore our output is 1. Now please pause this video and try to think of a function that takes an array as an argument and returns length of the longest consecutive subsequence. We are going to talk about two solutions of this problem. One solution is going to be the naive solution. In the naive solution, we are going to use sorting, right? It is a hint for you. Using sorting, we can find the length of the longest consecutive subsequence in big O of n log n time. What happens after sorting is consecutive elements come together, and then by a linear traversal you can find the length of the longest consecutive subsequence. Now please pause this video first and try to implement sorting based solution yourself. Here is implementation of the naive solution. What are we doing in the naive solution? We are first sorting the array, right? After sorting we get all the consecutive elements together, like 2, 3, 4 come together, 9, 10 come together, right? After that we initialize our result as 1 and we initialize the current count of consecutive elements as also 1. What we are going to do is, we are going to begin with the second element. For every element, we are going to compare it with the previous element. If it is one more than the previous element, then we increment the current. For example, for 3, we increment the count as 2, right? Current count as 2. When we come to 4, we increment the current count as 3. When we come to 9, we notice that 9 is not one more than the previous element. So what are we going to do? We have the current value as 3. We are going to compare this current value with the result and update the result, right? Our result is going to become 3. Why here? Because this is the beginning of a new consecutive subsequence, right? And we have result for the previous consecutive subsequence at this point. So at this point, we compare the result with the previous current, right? And then update the current to 1. So when we come to 9, we update the current to 1, and before that we update the result to 3. When we come to 10, right, in this we are traversing in the sorted array, right? So when we come to 10, what we do is we update the current to 2 because 10 is one more than the previous element, right? So current becomes 2. Now after 10 there are no more elements. So at the end we again check if the current value of the current, right, is more than result or not. Suppose there were 11, 12 more, right? Then the current would have become 4 once you come out of the loop, right? So that's why you would want to compare the current with the result at the end also. So this is Java implementation of the approach. This is C++ implementation. And both the implementations, we have first sorted the array, initialize the resultant current as 1, 1, then run through a loop. For every element, we compare it with the previous element. If it is one more than the previous element, we increment the current. And the trick here is we begin from the second element, right? Because there is not going to be any previous for the first element. And here is a check that we are doing for same elements. Suppose you had an array 3, 3, right? And then 2. After sorting, you would get 3, 2, 3, 3, right? What will happen? You will begin from here, your current will be 2. Now you come here and you see that 3 is same as the previous element. In that case, you do not want to consider this 3 as a beginning of a new consecutive subsequence, right? You want to ignore this 3 basically, and you don't want to count it in the result also, because in the result we are expecting distinct elements. So this 3 comes, we are simply going to ignore it, and suppose there was a 4 also after it, say there was a 4 in the original array, then we are simply going to ignore this element, and then we are going to move to 4. So to ignore the element, we check for this condition. We handle two elements only. We process two elements or two types of elements only. One which is one more than the previous, one which is not same as the previous, right? And we simply ignore the equal elements. So this is how the solution works, and the time complexity of the solution is clearly big O of n log n because we are sorting the array first. And auxiliary space is arguable. If you are allowed to modify your input array, then you don't need an auxiliary space. Like I haven't created an auxiliary array, but if your array is immutable, input array is immutable, you are not allowed to modify it, then you can say auxiliary space is big O of n or theta of n. Now please pause this video and think of a hashing based solution that finds the required length in linear time. Before we talk about efficient solution, let me give you some hints so that you can try implementing yourself first. So what are we going to do here? As you must have guessed, we are going to use a hash table and we are going to insert every array element into the hash table. For example, if you have this array, then your hash table is going to store only distinct elements, which is fine because we are expecting result as 4. 1, 3, 4, 2 is the longest consecutive subsequence, right? So once you have elements in the hash table, and these elements might be in any order into the hash table, how do we find out length of the longest consecutive subsequence using this hash table? One more hint for you is we are going to do 2n lookups into the hash table to find the required result. And how do these 2n lookups work? See, what we are going to do is we are going to traverse through the hash table. For every element, we are going to look for x minus 1. Say x is the current element in the hash table and say x is 1, right? It's the first element. What we are going to do, we are going to look for 0 into the hash table. 0 is not present, so we realize 1 is the first element of the subsequence beginning with it. Now we don't find 0, we know that 1 is, if there is a subsequence that includes 1, right, then 1 has to be the first element. Now what we do is we search for x plus 1, we find 2, right? We search for x plus 2, we find 3. We search for x plus 3, we find 4. Now we search for x plus 4, which is 5, we don't find it. So at this point we realize that we have a subsequence of length 4 in the original array or in the hash table, right? So we update our result as 4. When we come to 3, what happens is we search for 2 first, and 2 is present in the hash table. When x minus 1 is present in the hash table, at that point we realize this is not the first element of its longest consecutive subsequence. If it's not the first element, then first element must be present somewhere else in the hash table. And since we are considering all the subsequences beginning with the first element, we don't need to process 3. As soon as we look for 2 and we find 2 in the hash table, we don't process 3. We don't do anything for 3. Same as for 4. For 4, 3 is present in the hash table, so we don't do anything. For 2, 1 is present in the hash table, we don't do anything. For 9, 8 is not present in the hash table, so we are going to process 9. What are we going to do? We are going to search for x plus 1, which is 10, and we are going to find 10 in the hash table. So 9 and 10, they form a subsequence. We update our current result as 2, right? And our final result so far is 4, right? We have found a subsequence with length 4. After 10, we are going to search for 11, and 11 is not present. So we are going to keep our current as 2, and we are going to update our, compare our current with the result, and result is 4. So we are going to keep the result as 4. We are going to discard the subsequence. And after 9, we are going to come to 10. And since 9 is present in the hash table, we are going to ignore 10, like we ignored 3, 4, 2, right? That's the idea. So for every subsequence, it must begin with an element, right? And what are we doing in this approach? We are looking for beginning elements, and then we are looking for elements after them, and this way we figure out every subsequence because we are looking for every beginning element. Now you have good enough idea. Please pause this video and write the complete function yourself. Here is implementation of the efficient approach. This side we have Java implementation, and here we have C++ implementation. So what are we doing in this implementation? We are first building a hash table, a hash set in Java, and an unordered set in C++. So the hash set has distinct elements. After building the hash table, we are traversing through the hash elements, right? We have a loop in both the implementations, this loop here and this loop here. Now what are we doing inside this loop? We begin with the first element, whatever order we have in hash. Please remember, this order is not predictable. It can be any order, not even the same as original array, right? Hashing can store the elements in any unpredictable order. So I am assuming an order here, right? We begin with 1, and when we begin for x equal to 1, what we do is, as I discussed earlier, we look for 1 minus 1, 0 into the hash table, right? We look for x minus 1 into the hash table, and if we don't find it, right, if we don't find it, then what we do is, we know this is beginning of a subsequence, so we need to look for elements ahead of it, right? So for x equal to 1, we don't find 0, we look for 2 and we find 2. When we find 2, we increment our current subsequence length to 2. Then we search for 3, we find 3, we increment the current subsequence length to 3. And when we are at 3, we search for 4, right? This while loop runs for every element after incrementing the current. So we search for 1 plus 3, 4. And 4 we don't find, right? So we come out of the loop, and we come out of the loop. When you come out of the loop, what is the value of current? Current is 3. So you are going to update the result to 3 because result was initialized as 1. So at this point, our result becomes 3. Now we go to the next element in the hash table, 3, right? So this inner loop is over. We begin the next iteration of the outer loop. We go to 3. When we come to 3, the first thing that we do is we look for 2. We find 2 in the hash table, so we don't go inside this condition, right? So for 3, we simply ignore it. For 9, we find 8 in the hash table, so we ignore 9 also, right? For 3, 9, 2, what is going to happen? We are just going to check for this condition, and we are not going to enter inside this condition. After processing these 3, we come to 8. When we come to 8, we don't find 7 here, right? So we come here. We have current as 1. Now we run a loop. We look for 9. We find 9, so we set the current as 2. Now we look for 10. We don't find 10, so we don't proceed further. We compare this 2 with the current result. Result is 3 and this is 2. So result is not updated, but we have a subsequence of length 2, right? And when we come out of the loop, we simply return the result. Result is 3 for this example. Let's now understand how is the time complexity of this solution linear. How are we getting linear time? So if you take a look at the implementation, you can clearly observe that the first step is linear, right? We are doing theta n work because we are inserting every element into the hash table, and we are doing theta n work in this implementation also. After doing this linear work, we have a loop, and inside this loop we have another loop. So it looks like quadratic, right? But we are doing linear work. And there is a claim, if there are n items in the hash table, then we are going to do 2n lookups. So if there are n items in the original array, then there might be less items in the hash table. But n is, if we say number of lookups, it's in terms of hash table size. And we are going to show that if hash table size is say m, then we are going to do 2m lookups into the hash table. Let's understand with this example. So we traverse the hash table. When we come for 1, how many lookups we do for 1? We do 4 lookups. We do lookup for 0, then we do lookup for 2, then for 3, then for 4, right? For 3, we do only lookup for 2. We find 2, we do not go inside this loop. For 9, we do only 1 lookup. For 2, only 1 lookup, right? For these 3 elements, we do 1, 1, 1 lookup. For 8, we are going to do a lookup for 7, then 9, then 10. So we are doing 3 lookups. So how many total lookups we are doing? 4 plus 3 plus 3, 10 lookups. And what is the size of this hash table? 5. So number of lookups is twice the size of the hash table. Here are some more examples to prove that the number of lookups is twice the size of hash table. For example, here when we go for 1, we look up for 0, then we look up for 2, 3, 4 and then 5. So we are doing total 5 lookups. Here we are doing 1 lookup. We look up for 2, we know 2 is present, we ignore it. For 4, 1 lookup. For 2, 1 lookup. So we are doing total 8 lookups and we have 4 elements in the hash table. In this example, we are doing 2 lookups for every element. For 8, we look up for 7, then we look up for 9. For 40 or for 20, we look up for 19 and then for 21. For 4, we look up for 3 and then for 5. In this example, we are doing 4 lookups for x equal to 2, right? We look up for 1, then 3, then 4, then 5. For 4, we are doing 1 lookup, we look up only 3. For 8, we are doing 2 lookups. We look up for 7 and then we look up for 9. For 3, we are doing a lookup for 2, right? Only 1 lookup. Again, we have total 8 lookups. How does this formula work? See, for the elements which are part of a subsequence but not the first elements, we do always one lookup. For example, for 3, 4, 2, we did 1 lookup, right? And for the elements which are part of a subsequence and are the first elements, what are we doing? We are doing 2 plus len minus 1 lookups, where len is the length of the subsequence beginning with that element. For example, here for 1, how many lookups we are doing? We are doing 5. What is the length of the subsequence that begins with 1? It's 4, right? 1, 2, 3, 4. So how many lookups we are doing? 2 plus 3, 5. How did we get 3? Length minus 1. In this example, what is the length of the subsequence that begins with 2? 3. So how many lookups we did? 2 plus 2. 2 plus 3 minus 1. And in this example, every element is the first element and length is 1 for every subsequence. So how many lookups we are doing? 2 plus 1 minus 1, 0. So 2 plus 0 is 2, right? So 2 lookups we are doing for every element. And that's how we can say that the overall time complexity is linear for the solution.